Hello, so we're back. So we continue with the estimates. So the point of this section now is to sort of develop the estimates more, and in particular, we're going to choose a special test function. It's what is called a cutoff function, which would help us sort of set the stage right for the iteration process. Okay, excuse me. So this is where we left off so far. So the first part is more of an introduction and like standard ways of working with the estimates. So we have this estimate here. Okay. So what do we do now? So remember that the point is to get an estimate where you have like a comparison of L2 norms, and at this point we kind of don't have that yet. This is a gradient, and we have like other terms here. Okay, so let's work with those. So let's start first with this term. So to deal with that, we recall first the Sobolev inequality. And what that is that we have this one. So integral over b1 of v zeta to the 2 star 1 over 2 star is less than or equal to some constant dependent on n, integral over b1 of gradient v zeta squared to the 1/2. Okay, so here 2 star is, so for n bigger than 2, 2 star is equal to 2n over n minus 2. This is obtained from, so you have 1 over 2 star must be equal to 1/2 minus 1 over n. So here p is equal to 2. And for n equals 2, 2 star is any arbitrary number bigger than 2. Okay, so with this in mind, let's focus on this term. Okay, do I have space? Okay, let's erase some stuff. Okay, so this is the Sobolev inequality. I'm gonna erase it so that we have space. Okay. So the term is, I have, so integral over u bigger than k of absolute value of f v zeta squared. Okay. So if I have the condition that zeta is non-negative and less than 1, then we had that this is less than or equal to u bigger than k of absolute value of f v zeta. So zeta squared is less than zeta. Okay, so we've seen this before. What we're gonna do is, so for brevity, do I want to do that? Oh, no, okay, we're not yet done. Okay, sorry. So I'm gonna write this then as integral over b1 of absolute value of f v zeta times the indicator function of u bigger than k. Okay. Now, so we know that this is in LQ. We're gonna apply the Sobolev inequality to v zeta. So we give this like a 2 star contribution, so that if we want to use Hilder, this would be, we estimate this as something in L alpha, where we have 1 over alpha is 1 minus this one, a reciprocal of this one, and the reciprocal of this one. So 1 minus 1 over q minus 1 over 2 star. Okay? So now we apply the Hilder inequality. So this is less than or equal to LQ norm of f times the L2 star norm of v zeta times the L alpha norm of this, which would just be the measure of the set u bigger than k raised to 1 over alpha, which is 1 minus 1 over q minus 1 over 2 star. Okay. And then we apply the sublevel inequality. So the sublevel inequality would say that this is going to be less than or equal to some constant c dependent on n times the L2 norm of grad of v zeta. And this is less than or equal to some constant LQ norm of f times the L2 norm of v zeta times this one. So note that, okay, so I'm gonna write this as the measure of the set where v zeta is not 0, okay, and we're in B1, okay, and this is raised to, what do I have here? So if you just do the algebra, this one here is equal to, I'm just gonna write it down, it's 1/2 plus 1 over n minus 1 over q. I'm gonna write that here. 1/2 plus 1 over n minus 1 over q. And I would also want to point out that this set is the same as the set where u is bigger than k, of course in B1. Okay. So what are we gonna do now? So L2. So what do you know of this term? These terms appear in our estimate. It's this one. So we can do that trick again of Cauchy's inequality with a small constant delta, so that we can move it to the other side. So doing that, this is less than or equal to some delta times grad v zeta squared. And note that this is, of course, going to be 0 outside u greater than k. So this is just equal to that, even though that this is in B1. Plus some constant dependent on n and delta. N came from the sublevel inequality. This to this. Okay? Times LQ norm of f squared times this quantity squared. So you have measure of v zeta not 0 raised to 1 plus 2 over n minus 1 over q. Okay. And note that if this is small, then this is going to be less than or equal to something with a smaller exponent, and that is 1 minus 1 over q. And that is fine. We are in B1, so that you know that this is going to be sort of comparable to a constant just dependent on n, which can be absorbed into this one, times 1 to the dimension d. So this inequality would be true. Okay. So we have this, and the reason we're doing this like Cauchy's trick with delta is we're going to put this in the other side, combine it with this. Okay. So there's that. So doing that, what we eventually get is this estimate. So we have the integral. So we're omitting, so we omit this for brevity. So we don't have to keep on writing them. So what estimate do we have? So integral of grad of v zeta squared less than or equal to some constant v squared grad zeta squared plus I have here c v squared zeta squared plus k squared c zeta squared plus f squared times measure v zeta not 0 raised to 1 minus 1 over q. Here, f is defined to be the LQ norm of little f. Okay? Okay, so remember, what's the point? We want L2 norms. We have sort of taken care of this term here. Okay, so we see how the idea is it possible to get an estimate where instead of these terms here, you have something like this. So you have something like k squared plus f squared times this one. Okay, that is what we're going to work with. 1 minus 1 over q, provided that this is small. Okay? Okay, so, and in fact, that is our claim. So we claim that if this is small enough, we have the following estimate. Grad of v zeta squared less than or equal to constant v squared grad zeta squared plus k squared plus f squared. What's this? V zeta not 0 raised to 1 minus 1 over q. Okay, so to do this, we need to estimate the terms with the c. Okay, so let's do that. Okay, so this is fairly standard again. So of course you can try and pause here and see whether you can get the estimate. It's standard. You just use like subsolute inequalities and stuff like that. Okay, so you can pause and try for yourself. Okay, so let's do it. So the first term is this one. Okay, so I am gonna write this as c v squared indicator function. V zeta squared indicator function of the set where v zeta is not 0. So I know that c is in LQ. Okay. This is squared, so I want to use solvable inequality. So I kind of want to cancel out the 2 exponent. So I'm gonna put this in L of 2 star over 2. So note that the optimal is 2 star. That's the largest, so 2 star over 2, that's fine. It's below 2 star, which leaves us that we estimate this term as being an element of L alpha, where 1 over alpha is equal to 1 minus 1 over q minus the reciprocal of this term, which is 2 over 2 star. And did I compute that? That is equal to, what do I have there? 2 over n minus 1 over q. So it's just algebra. So this is equal to 2 over n minus 1 over q. Is that right? I think. Okay. So with those, we use Hilbert's inequality. So this is less than or equal to LQ norm of C times, what would this be? So I have integral of v zeta squared raised to 2 star over 2 over 2 star. So this is why we use 2 star over 2, so that we can cancel out this one here. Okay? Okay. Times the measure of v zeta not 0 raised to 2 over n minus 1 over q. Okay? And now, what are we going to do next? We're going to estimate this using the Sobolev inequality. So by the Sobolev inequality, I know that this term is less than or equal to some constant times grad of integral of grad of v zeta squared raised to 1/2. But note that this is raised to 2 already, so that cancels out the 1/2 here. Okay. So this is less than or equal to some constant CLQ. Let's write it as grad v zeta squared times the measure of this set raised to 2 over n minus 1 over q. Okay, so what are we doing? We're trying to deal with this term. Okay. Is that what I want? Okay, so we stop there. Now let's look at the other term with the c. What is that? It's this, oh sorry, we just dealt with that. It's this one. Okay. So to handle that, so I have integral of, what's that? So k squared integral of absolute value of c zeta squared. So this is, so same trick. Note that this is an integral over this. So I can write this as k squared integral over b1 c zeta squared, indicator of v zeta not 0. So we have the assumption that zeta is less than or equal to 1, so this is less than or equal to 1. Zeta squared is less than or equal to 1. Note that we're not applying solvable inequality here because there is no v. V just appears here, and that's fine. Okay, so solvable inequality on v zeta, if v is present, if it's just zeta, you use a pointwise estimate on zeta. It's less than 1. Okay, so now this is in LQ. This is in this is in LQ. So we estimate this as in this is in LQ prime, where Q prime is 1 minus 1 over Q. 1 over Q prime rather. So this is less than or equal to k squared times the LQ norm of C times the measure of v zeta not 0 raised to 1 minus 1 over Q. So we have that. Okay, so combining, so combining this and this, so you put it where? You put it here, what do you get? So combining everything, we get integral of grad v zeta squared, okay, less than or equal to c times integral of v squared grad, why is my pencil malfunctioning, grad zeta squared plus, okay, what do we have? We have integral of grad of v zeta squared times the measure of v zeta not 0 raised to 2 over n minus 1 over q, plus k squared plus f squared times the measure of v zeta not 0 raised to 1 minus 1 over q. So we literally just included these estimates here. So yeah, I do hope that when you're watching this video, you're also sort of doing the calculations together with me so that you see for yourself like how the calculations play out. Okay. So what are we gonna do now here? Remember that we are under the assumption that the measure of this set is small, and that assumption comes into play by, so what we do is, well, what can you say about this one? This is that term as well. So standard thing to do, okay, so you put that here. If this is small, then the resulting term in this side would be positive. Okay, thus, if is small enough, you can move that to the other side and eventually get something like this. Zeta squared less than or equal to some constant times v squared grad zeta squared. So we don't have this anymore, plus k squared plus f squared times the measure of this set, not 0, raised to 1 minus 1 over q. Yes, which is the claim. So the claim is now proven. Okay. Okay, so what do we do now? So we're almost with the estimate that we want. How so? Well, this just looks like an L2 norm of V. Just we have some other terms here. Now we want the L2 norm of V to appear in this side, so we're going to apply solvable inequality here. So to do that, let's use orange. Okay. So we deal with this term. So the integral of v zeta squared on the set over the set u bigger than k, this is equal to v zeta squared, sorry, v zeta squared, indicator v zeta not 0 over b1. Okay, so what we're gonna do is I'm gonna assign this to L of 2 star over 2. So we want the solvable inequality to relate the L2 norm of V with its gradient. So with that, this now gets alpha, where 1 over alpha is 1 minus 2 over 2 star. Do I compute this? This is just 2 over n. Okay. So by Hilder, this is less than or equal to the L2 star over 2 norm of this. No, wait. Okay, so what do I have here? This is going to be less than or equal to integral of v zeta squared raised to 2 star over 2 over 2 star times the measure of v zeta not 0 raised to 2 over n. 1 over alpha is 2 over n. So this cancels out. And then you use the solvable inequality. So by solvable inequality, this is less than or equal to some constant times grad of v zeta squared. So again, the 1/2 cancels out because this is already raised to 2. Okay? Times the measure of this, not 0, raised to 2 over n. Okay, so what do we have here? This is controlled by this, but everything that we've been doing so far is trying to control this term. So we have a control on this term now. Okay, so again, so this is controlled by this, but this is that, and it's controlled by that. So combining everything, what do we get? So we get that v zeta squared over u bigger than k is less than or equal to some constant c times, okay, what do I have here? Measure of v zeta not 0 raised to 2 over n times v squared, this is grad zeta squared, plus we have v zeta not 0 raised to 1 plus 2 over n minus 1 over q times k squared plus f squared. So we literally just plug in the estimates that we know. Okay, so with this, note that there exists some positive epsilon, so that this is going to be less than or equal to c. Instead of dealing with 2 over n minus 1 over q, you have, this is epsilon, and I leave that as an exercise. It's easy to like argue that such an epsilon exists, plus this raised to 1 plus epsilon k squared plus f squared. Okay, so we have this. Provided that, of course, this is small enough. So if is small enough. Okay, so now we have an estimate where the L2 norms of V zeta sort of appear, or the L2 norm of V appear. So what we're now going to do, and this is fairly standard in things like these, is, to choose a particular test function zeta. So in the literature, it's called a cutoff function. So far we've assumed that zeta is, non-negative and it's less than 1. So now we're going to choose zeta so that we can say something about its gradient. So to do that, so this is choice of zeta. So to do that, let 0, let R be positive, smaller than big R, less than or equal to 1. So the choice of zeta in C10B1 would be like this one. Okay. So this is some kind of a heuristic thing, and it can be made precise. We're gonna say how later. Okay, and suppose this is minus R, this is R, this is minus big R, big R. So I am going to choose zeta such that, let's see, this is 1. I'm gonna choose zeta such that it's equal to 1 in the region minus R to R. So in the ball of radius R centered at 0. So it's 1 there, and then it's going to decay to 0 such that it's equal to 0 now at R. So on the boundary. Okay. Now, it's going to decay in such a way that it's still going to be in C1. So this is going to be zeta. So zeta is 1 in BR, 0 less than equal to 1 in BR, and that zeta is in C10BR. Moreover, we want a control on the steepness. So as you can imagine, if little r is close to r, if zeta is to somehow vanish starting from 1, if little r is close to r, it's gonna be steep. So the change from 1 to 0 is gonna happen fast. So it is sort of reasonable to say that the gradient of zeta, the control that we have on that, is going to be some constant, and it's dependent on the distance between r and little r. Now there is a construction for zeta, such as zeta, and it involves like using modifiers. So maybe at some point we're going to talk about that, but for now, let us be contented with the fact that we can choose such as zeta, and it makes sense that the control on the gradient sort of blows up. We lose control as little r goes to r, and it has something to do with the steepness. And I hope that makes sense. So if r is far from big R, then it can be like less steep. But if r is close to big R, then if you want the function, it's starting from 1, and then you want it to be 0 at r, it has to like change quickly. It's going to be steep. Okay, and the steepness is a measure on the size of the gradient. Okay. Okay, so we choose such a zeta. So with that choice of zeta, what can we say? We can now estimate this term. So we have this is controlled by this times this. So now we can estimate this term. Okay. So for such a cutoff function, so it's called a cutoff function because it's 0 as if you're close to the boundary, and it's like just 1 at some like small set contained in your set. So for such a cutoff function, let's see. So what do we have? We have now v zeta squared. So this is in u bigger than k intersect br. Note that the support of zeta is in br. This is less than or equal to some constant time. So we are going to estimate this term. This is controlled by this is sort of proportional to 1 over big R minus little r. So less than or equal to some constant, 1 over r minus little r, and now we just have v squared. U greater than this intersect br times v zeta not 0 raised to epsilon plus k squared plus f squared v zeta not 0 raised to 1 plus epsilon. Okay. And now what we do is, let's use pink. Let's look at this one here. Now the question is it possible to just make this a term with just v, no zetas? And yes, we can, because we know that zeta is 1 in b little r. Okay, so this is bigger than u over this, intersect b little r. Why is that? Because this is a subset of that. And then I have here v squared zeta squared. And in this set, zeta is equal to 1. So this is the same as v squared intersect br. And that this is, note that v is equal to u minus k squared u greater than k intersect br. So I am gonna call this set A of kr. So just notation, it's gonna help us later. So again, so v is just u minus k in this set. This is just A of k big R. So with that notation, we have that, what do we have? We have integral of u minus k squared over a k little r is less than or equal to some constant times 1 over r minus r. I think this is squared. Did I square it? No. It's squared because the gradient term was squared earlier. And I have here u minus k squared a of k big R times the measure of a k big R raised to epsilon plus k squared plus f squared times measure of akr. Note that akr is the set raised to 1 plus epsilon. Okay, so we have this. And this is for, this is true if a of kr is small enough. So we've been saying that thing over and over again, if the measure of the set is small enough. So we're going to show now that it's actually possible to choose some k such that this set is going to be small. And how do we do that? Okay. So note, so we choose k such that this is small. And to do that, okay, note that, okay, let's see, integral of u over u bigger than k intersect br. Note that this set is equal to a of kr. So in this set, u is bigger than k. So this is bigger than k times the measure of this set. So which is measure of akr. Thus, the measure of akr now is less than 1 over k times this. Note that k is positive, so this is just equal to 1 over k, u positive part, and this is less than or equal to 1 over k times the L2 norm of u plus. Note that BR is contained in B1. Okay, so I have something like this, maybe some constant here, L2 norm, B1. Okay, so what do you have? If k is large, this is gonna be small. So you know that there exists some k0 such that for k bigger than k0, a of kr is small enough. Okay, so, and remember that the estimate that we've derived only holds provided that the measure of akr is small. And now we've seen that, yes, there exists a big enough k such that the measure of that set is small. And what is that saying? It's saying that there is some constant k such that the parts where u is bigger than that is just small. Okay. But eventually our goal is something stronger. The goal now is we can show that there exists some big k such that the integral of u minus k squared over ak 1/2 is equal to 0. So this is the big thing which would give us the boundedness. And what this means is that u is less than or equal to k almost everywhere in b 1/2, which is the goal. U positive part. Okay, which is the goal. So that is it for this video. What we're gonna look into next is the actual iteration process. Okay.